Good afternoon, everyone. Thank you for taking time to join us today. Welcome to our webinar, A Powered Engineering, Why Your 2026 Workflow Starts Without a Mesh. So for years, meshing has been at the core of simulation workflows and at the same time, one of the biggest bottlenecks. It demands time and expertise and often, multiple iterations just to get to a stage where meaningful analysis can begin. So for many teams, this slows down the innovation more than it enables it. Today, the reality is being challenged, and with the emergence of AI-driven engineering, particularly solutions like Siemens SimCenter Physics AI, we are seeing a fundamental shift from geometry to mesh, then mesh to solve, and to directly geometry to insight. So this is not just an incremental improvement; it is a transformation in how engineering decisions are made. So at Messen Labs, we have been working closely with organization to bring this transformation into real world workflows. Our focus is not just on adopting new tools, but on helping teams rethink their process, leveraging AI to drastically reduce simulation turnaround time, enable faster design iterations, and make high fidelity insights, accessible earlier in the design cycle. So in today's session, we will cover how AI, specifically physics AI, is redefining simulation workflows and where this fits alongside traditional solvers, not as a replacement, but as an accelerator, but and how Siemens is helping engineering teams transition to this new paradigm. And by the end of this webinar, we hope you will see not just where the industry is heading, but how you can start, taking practical steps towards it today. And meanwhile, if you have any queries, please feel free to drop it in chat and let's get started.
So, hi, thanks for this introduction. And myself, Ankit Vadikhai, and I'm an application engineer working at Messen Labs for structural solutions. So, the agenda for today is going to be first of all, we are going to see what general overview is for physics AI, and then the technology behind it, why is it faster, how it is, what it is doing in the backend, and things like that. Then we'll see a general workflow of how starting from the setup of the physics AI model, training the machine learning model till the prediction, how it is going from step by step. And then it's not just about predicting the contours, but it's more than that. So we'll see that as well in the custom inputs and custom outputs sections. And finally, we'll have some time for discussions as well at the end of this webinar. So as Sujit also mentioned, if you have any queries in the middle of the session, please feel free to put it in the chat box and we'll be happy to answer. So before moving forward, I'll just show this video. So for people who are already, a CAE engineer, FE is their day-to-day work, they can easily understand that this is just a CAD, and from going to CAD to the prediction is they understand how time consuming that process is, right? So starting from the meshing till, maybe geometry cleanup, connecting and all those things, you do all those things one by one. And finally, when you trigger the run, you get to the second side of the screen, right? So you get the results and all those things. So physics AI is able to do it with one single clicks and comparatively with very lesser time as compared to what your traditional FE solvers are going to take. Okay, so how it is going from screen one to screen two within just a click is what we are here for. We'll see what the technology physics AI is using it and all. So physics AI, by the way, is not just only one CAE plus AI product that we have. We have other things as well in our portfolio. For disciplinary design exploration, you have the hyper study. Then for design exploration, you have something called design AI, which is usable in the cloud as well as in the hypermesh as and the inspire. You have the design explorer which you can use on prem. Okay, then we have another data analytics platform called rapid miner. Now it is called AI Studio, and it is again a low code, no code type of data science platform which uses parametric data to predict the parameters. Then we have Shape AI, which is for the geometry recognition. Then we have Rome AI, which is for system identification and basically reduced order modeling. And then finally, we have Physics AI as well that we are here for. So let's get started with the overview first of all. Okay. So how physics AI is different as compared to the other machine learning algorithms is, let's say you use any of the general machine learning algorithm that is there in the market. So it will use a structured data. It will have explicit parameterization and some variables that are of some values. And when you feed those data, structured data to machine learning models, it will either give you a scalar prediction or or a curve or vector prediction. Right. What physics AI is capable is you can either have a structured data or you can also have a contour result data, basically for the CA engineers, right? So you can have that unstructured data as well, or the structured data, you can feed it to physics AI and it will be able to give you the field predictions as well as what conventionally any ML language can give you, that is your scalar and vector predictions. So that is where your physics AI will be there for the engineers, the CA engineers as well. So, what physics AI is able to do is basically because of something called GDL. GDL stands for geometric deep learning. So the main brain behind the physics AI is what geometric deep learning is. So it learns directly on whatever the existing simulation data that you're having with you. Okay, so many of the R&D centers or any big organization may have data that they have been using or they might have simulated and got results out of it. Okay, so those existing data that is sitting in your directories can be made use in physics AI by training the machine learning model and further making physics predictions on the new design that you get. Okay, the workflow is very intuitive for physics AI. It's not like very complex that you see in any of the other machine learning algorithms or workflows. So it necessarily have some 4 or 5 dedicated steps that will cover all your physics AI workflow, and finally, you will be able to do the predictions as well on the new design. So how this 3D mesh is being used? Okay, so let's say you have a CAD, okay, and on that CAD you might have meshed it for a particular scenario I'm speaking. So there might have been a time when you might have a CAD and you have had the mesh onto it, and then you simulated it and extracted out some results out of it. Okay, so this scenario is one scenario. You can have thousands of such scenarios, which would have yielded you thousands of result files corresponding to each and every design change or the design different geometry, right? So for each of the result files that you have for every scenario, you would have nodes and the features onto that node. So features as in the position of each and every node, basically the X, Y, and Z coordinate, and then how each and every node is getting connected to one another, and then on each and every node what is your output. So on the result files you would have either a stress data or a displacement data onto each and every node, right? So when you feed in all of these data to physics AI, it is going to look for patterns. It is going to look for what results are varying in each and every data set that you have provided. And based on that, when it learns, it is going to give you predictions onto the new design with a new variation of the geometry. So that is how your physics is going to relate to the nodes and the connections and the position and the respective labels of the output. So what basically is used is something called an architecture. Okay, for machine learning, there is something called an architecture that it uses in the backend to train the models based on different type of data that you provide. Okay, so when physics AI was just launched, it had the very first simulator called the GCNS, GCNS stands for nothing but your graph context neural simulator. Then came the transformer neural simulator. So after the transformer neural simulator, the recent one was the shape encoding regressor (SER). So these all these algorithms are one way or the other from each other. Okay. So your GCNS, which is the legacy one, is basically based on your graphs. Okay. So it has the nodal coordinates extracted from the data set and the outputs that we saw. Okay. And then it is faster on the CPU if you have a CPU infrastructure with you. And then there is the TNS mechanism, which is basically on the attention mechanism. Okay. And this one is faster on GPUs as compared to the earlier one, the GCNS one. And then the prediction that you do with a TNS trained machine learning model is going to provide you a very smooth contour for the predicted data. Okay, so this is as compared to the GCNS. And then finally, there is the latest one, which is launched, the shape encoding regressor. So shape encoding regressor basically works on your vector outputs. So if you have some key point indicators or the curves that you want to predict, so those predictions you can make using the SER algorithm at the backend, but it will not yield you the field data. It will not give you the results on the predictions. Okay. And then it is much faster as well because it is not, since it is not generating any of the field data for as prediction, it is faster as compared to the TNS and the GCNS. And also it is more stable that we have seen. So the domains that are catered with physics AI is you can go with structural, you can go with crash, aerospace, thermal, fluids, NVH, and majorly everything is covered here. And one more thing to add here is that you can have any of the result files that may be of any solver, maybe Nastran or OptiStruct or Radios file. Only condition is that whatever the result files that you have for the data set as a data set should be readable in the hyperview. Even if it is not readable, you can make use of HV-trans. There is one tool called HV-trans that you will be able to translate your result files into the optistruct.std format. So you can make use of that uh, result file and convert it into std and then train your physics AI model. So the analysis that are currently supported is linear, nonlinear, transient, and statics. Then buckling, fatigue, thermal, electromagnetics, manufacturing processes, and of course the fluid flows. And basically, how physics AI is going to help you accelerate your design iterations is, let's say, for a traditional process, everyone knows that there is some requirements that you set first of all. Then you go with the design, concept designing. Once the concept designing is there, you explore, then you optimize, then you validate, and then the final design comes. But in this full traditional process, there is an iterative process. So that iterative process is exploration, then optimization, then validation. So it is very much iterative and it will consume a lot of your time, isn't it? But with physics AI, when you leverage it, you just have to set your requirements. Then you add your data, what you already have with you, the result data, and then you train your model, and then you get some inference from it. And once you get some inference from it, you can validate it with the high fidelity simulation. And once you validate it, your final design is here. So that iterative cycle that is there in your traditional process is going to be eliminated here in physics A. And then when you get some more data, you can add that as well. So we'll talk about it as well, how you can add your new data into the training. So this is what the transfer learning is. Okay. So let's say you have, first of all, some five results and you trained your model on those five results with those geometric changes. So when you train it with those five, it will have some. uh, accuracy as the one which is shown in the uh, graph above. Okay. Let's say after that, after training your model, you get one new design, one more design that you think you can add into the existing trained machine learning model. So at that time, you can make use of the transfer learning option here. You add that new sixth design as well in your training data set, and then you retrain your model. So once you retrain your model on further data that you got, you will have some improved accuracy, and your predictions will be much accurate as compared to the ones when you trained it with the first five data set. So you can do that as well. It's not like you just train it once and then you have to only utilize those pre-trained model. You can add further data as you get from further simulations. So that was the overview. Let's see how the general workflow goes. So from data to deployment, first of all, you have the data. You collect that historical data, or else if you don't have the data, you can also generate synthetic data. For that, we have hyper study and design explorer. You can generate that synthetic data, and then you prepare the data. You do the cleaning, pre-processing, and all. Then you split it into the training as well as the testing data set. Once you have the data prepared, you go with the model training. Excuse me. So in the model training, you generate the physics AI model. First, the very first training that you do should be on the already existing default parameters that it has. And then once you get the result, you can optimize the hyperparameters. You can fine tune your model parameters for better performance. So our accuracy can be further increased once you get the preliminary ML model accuracy. Once you optimize your hyperparameters, you can go with the model testing. So whatever the data that you would have kept for testing, you can use that to test the accuracy of your machine learning trained model. And then finally, once you are satisfied with the accuracy results and the metrics, you can go with the model deployment. So what type of data collection? For example, right now here you see there is a hood, a car hood, and there is an impactor. So for all of these data, these are 20 data sets. And for all of these data sets, the location of the impactor that it is going to hit onto the hood is differing, correct? So these are the different design variations that you see. And when you pull in this data to train physics AI model onto it, it will generalize the model and it will generalize the patterns that it sees in the data set. So next time when you want to see the results for a new head impactor location that it is not there already in the data set, you just feed it here and then you make the prediction like we see in the very first slide, if you recall. So, so that particular slide was telling you if you have any new CAD with the new impactor location, you can just make the predictions with one click. So the necessary condition for that is you need to have the machine learning model already trained with you. Okay. Then the data set is basically having a nomenclature. You have the training data set first of all, and then you have the testing data set. So within the training data set as well, you have further classification. First is your training, and then the validation. So both of these training and validation data set are going to be a part of your training procedure itself. Okay. So how your training procedure is going to be. First of all, you train the model on the training data set. Okay. And then the physics AI, without your intervention, will be able to evaluate the model during the training process on the validation data set. So when it is training, it is going to evaluate the model's accuracy as well on the validation data set that it has already extracted out. And as it gets the predictions from the validation dataset, it is further going to tweak the model according to whatever the results it sees on the validation dataset. And then it will again retrain the model. So all this happens with multiple iterations during the training procedure. Finally, when the training procedure is done, it will choose the model that will be performing best on the validation data set. And when it chooses that model will be taken into consideration for whatever the predictions that you make on your new designs. So that is how your training process is going to be. So how is your accuracy of the model that you are training is going to be determined? Okay. So there are multiple hyperparameters that you are uh, going to set when you are going to train the model. Okay. So as far as the model complexity is concerned, there are two things. One is your depth and the other is your width. Then for the training process, you have the learning rate, then you have the batch size, then you have the epoch, and finally you have the early stopping or the patience as well. So I'm not going to go in the details of it, but it is well enough written in the health documentation. So you can go through each of that. The as far as the model complexity is concerned, let's talk about the width as well as the depth. So basically, you cannot increase the width or depth too high because it is ultimately going to lead you to high resource costs. Okay. And it will also be computationally very expensive if you, without any thoughts, you just increase the width and depth of it. Basically, if you have low depth, low width, it is going to be very resource friendly, but the training accuracy might, get hindered. Okay. And if you have high width and high depth, it will again be very expensive computationally speaking. So this particular image, don't get confused. This physics AI does not uses images. It's just an analogy to tell you how the depth and width are varying. Depth and width are varying. So if you see, if you are increasing the width, it is going to capture more features. And if you are increasing the depth, it is going to capture more details. So this image itself speaks for it. I hope it is understood. So let's see a general workflow how physics AI is going to uh, train the model, test the model, and finally predict. So you have some design variations. This is a synthetic data that is generated. So upper and lower flanges are having variation in the angle, and these have 20 data sets. So you specify a project name as well as the location where your project directory is going to be saved. Then you go with the dataset creation, provide a dataset name, and point to the directory where all your data is going to be stored. Once you select the folder, all your data will be there. You can enable the train test split and then extract out the dataset. Okay. So once a dataset is created, you go with the model training, specify the name for the model that is going to be trained, and then the input and the outputs. So input is going to be your mesh data as well as the part labels, and output is going to be basically what you are going to predict. So once the model gets trained, you can see the log, you can see the data for epochs and the loss for each and every epoch, and then there is the loss curve as well. So once your model is trained, you test your model on the testing data set, and then finally, whatever the testing data you have, you can see the detailed report of how your trained model has performed on the testing data. After all this, you just set the model as active. Once the model is active, you can bring in your new new data, new design basically, import that design, and then finally click on predict. So once you click on predict, it will take seconds to minutes maximum, and then you will have your results predicted onto the new design. So that is the how the workflow of physics AI goes, starting from creating a directory till the end where you predict the results onto the new designs. Okay, let's talk about custom inputs and outputs. So the physics AI, as I said earlier as well, physics AI is just not limited to predicting the contours. It is more than that as well. You can predict the KPIs or the values as well as the curves. So that is where your custom input comes into picture. So custom inputs are also of two types. One is global, and then the other one is the nodal. So let's say you have some geometric variations, and with respect to all the data that you provide for geometric variation, you have any input that is going to affect your final results. Okay. So, but make sure that whatever the variations you are going to bring into picture does not changes the mesh. So the mesh data should remain as it is. Only the inputs that are going to affect your final results can be changed. So what are those kind of inputs? Those are, let's say, the shell thickness. Then there are material properties. Then there is force applied to a particular node across all the files. So like that, you have force locations, the initial conditions, the boundary conditions, the constraints. So all these can vary across all the files, and you can bring that into picture to train your machine learning model. So these custom inputs and outputs, there are further classification. One is the global input, and then the other one is the nodal input. So global input, basically the inputs that are going to vary across all the nodes for each and every model. So what are they? Let's say for three components, your shell thickness is varying across each file. Okay, so that can be considered as a global input. Then the material properties applies the same thing, and then the initial condition as well. The other thing is your nodal input. So nodal input is going to be the inputs that you provide for the particular node across all the data set. For example, there is node number 100, and on node number 100 across all the data set, you have the force magnitude differing. So you can make physics AI take that into consideration. Okay. So like that, you can have boundary condition variations, you can have constraints variations, you can have the locations of the forces that are varying, and all that can be brought into picture for better accuracy and making sure that physics AI interprets the pattern for the results that are associated to these variations. So let's see how your custom inputs can be taken into consideration for training your model. So again, you first of all create a project, and then you provide location where all your projects are going to be saved. So notice that in this, whatever the training files are there, each and every training file is having the same name convention with respect to the corresponding S3D result file that it has. Okay. So for example, run one is having one STD file as well as the JSON file. Likewise, run 7 is also having one STD file and one JSON file. So let's see what JSON file is carrying. So each and every JSON file is carrying a label and a role and a type. So role is basically input. If you are going with custom outputs, you would set it as outputs. So for let's say E and new, okay, the Poisson's ratio and the Young's modulus, you are having a certain data value that is there for particular result file. So if this is run 2 and you click on the JSON file related to run 3 or let's say the run 4, it will have a different E value. So you can feed that E value as well as in the form of the JSON file. So once you have all the JSON files corresponding to the result files, you can have a Python script. So this Python script, you are going to paste it into the hooks folder that it creates in your project directory. So basically, this is the name that we provided, the global hooks folder. And in this, by default, these particular folders are getting created. So that particular Python file, you just need to paste it into the hooks folder. So once you paste it in the hooks folder and then go with the dataset training, the dataset extraction, you just point to the location where all your data is, select the folder, and just see the std files and say OK. So once you have the data set, and then when you go for training, so when you go for training and train a new model, you will automatically see that in the inputs, apart from the mesh data and the part label, which are default, you will have further model data as well that you have specified in your JSON files. So we only specified the value of E and new for each and every data set. So those are here populated in the inputs. So you can make use of these also to set it up as inputs for physics AI to learn from them and see some patterns if these values are affecting your results. So the result thing remains as it is. You just specify the name and specify hyperparameters and finally train your model. So when you go for prediction, the only thing that you have to take care is for the new file, you will be having a new value of E and new, the Poisson's ratio and the Young's modulus. So that JSON files should be pasted in your hooks folder. So when you paste it in your hooks folder and bring in the new design, physics AI will consider the values that you have fed into the JSON files, and based on that, it will make the predictions on the new design. So that is about your global inputs. So this was about the global inputs. This particular Excel sheet is basically used for the nodal inputs. Okay. So instead of the JSON files corresponding to each and every data set, you just have to specify the Excel sheet as a file to each and every data set. So each Excel sheet will necessarily have the same node IDs that are there across all of them. And on these node IDs, you can specify the values that are going to change. Okay. So across each of the Excel sheet that you provide for each and every data set, you will have the fx, fy, and fz value varying. The node IDs remain same. So rest of the process remains as it is that we saw in the global inputs. The nodal inputs also remains the same. Only difference is that you specify Excel sheets instead of JSON files that you used to do in the global inputs. So this was about the uh, custom inputs. Let's talk about the custom outputs. So right now we were specifying the entities that is going to affect my results. What if I want to predict results that are not contours, but some key point indicators? Let's say the maximum value of displacement or a curve. Okay. So how you can predict those things are not native, but using the custom outputs, you can specify those things as well and then get your result outputs. So let's see how that basically works. So if you see here at the right side, you have a label and then you have a type called vector and then the data that is associated to that particular file. Okay. So if you have a big testing file, if you see left bottom side image, you will have on the A column, you will have all the result files. And for each and every result files, there is some value that is going to change for the B, C, D, E, and F column. So these testing files, you can make use of it for predicting the outputs that are related to the new designs. Okay. So let's see this in action. So you specify a project name as well as a location. So if you see with respect to each and every STD file, you again have a JSON file. And if you open this JSON file, this time you will see only one syntax change, that is the role. So if you see right now, the role is set to as output. So this output, if you set the role as output, it is going to predict the following datas. Okay. So for example, displacement I, displacement H, and then I1. These are the labels that you are interested to predict basically. Okay. And you set it as an output. So with respect to each and every std file, you already know what is the displacement I value, what is the displacement H value, what is the I1 value. Those you already know. So you just set it up as JSON files with respect to each and every std. And when you set it up, you just use this as the custom outputs. To go for creation of the dataset, specify the dataset name, point to the directory where all your data is, and then request those files and extract the simulation properties as well as train test split. Okay. Finally, when you go with the model training, you will see one more column here, one more option here, that is output for vectors. Okay. So here you have all the particular labels that you have set up in your JSON files. So basically, you are telling Physics AI that my input is going to be the mesh data, and based on that, I want to predict some particular vector data. So with this, you need not to select any contour for output and then just train your model. So for prediction, when you go with a prediction on onto the for the outputs, what you need to do is you just have to have a JSON files with the new values onto the hooks folder. So those hooks folder again, as we did in the global inputs, same thing you will have to do in the uh, custom outputs basically. Hope the idea is clear. So finally, these are some uh, case studies from our customers. So Lucid Motors had the airbag deployment. Excuse me. The Continental had the airbag deployment, and they found that the solver that was taking time for a particular physics predictions was approximately 2 hours, while the physics AI took only 30 seconds to predict the results with very good accuracy on the new designs. Then there is a case of Lucid Motors. Then there is Magna as well. So Magna was doing this Crashbox predictions, and they found that solver is basically taking 14 hours, while physics AI predicted their results within 10 seconds. And the accuracy was also highly appreciable. It was more than 97%. So how your simulation runtime is going to drop? Imagine that. If you have physics AI in action, if you properly train your model with good hyperparameters and have a good accuracy of your model, it is going to be very beneficial for you. And all you need is the maybe the data that is sitting in your local directories. So you can make use of that and train your physics AI model for predicting onto the new designs. So again, how your product has developed so far in the past decades. So earlier we used to do like not us, but people used to do physical testing, right? It would take them weeks or months, right? Then came simulation, which reduced the times to days. And then now we are basically integrating AI with simulation, and it is giving us much faster results. And our productivity is also increasing with that. So if you remember the very first video that we saw in the first slide, this is the continuation of that. Let's say if you want to see different iteration of the designs. So, so what you can do is you can just change this impactor location anywhere in this particular hood area, and then quickly click on predict, and it will give you the results. So this is very intuitive. You can, within the Hypermesh UI, you can change certain parameters, certain geometric variation, and the physics AI will update its AI predicted results, which is going to be faster and it is going to be accurate as well. So thank you so much for being a good listener. And the upcoming webinar is going to be on SimCenter Flow EFT. The topic of that webinar is going to be accelerating your control valve design using the SimCenter Flow EFD. It is on 12 March. Reserve your calendars for 3 p.m. to 4 p.m. on 12th of May, sorry. And we'll be definitely giving out the registration forms for you. I will wait for this particular one. And then there is going to be a SimCenter Technology Conference in Chennai this time. So we are hosting this SimCenter Technology Conference this year, and it's a bit of a milestone event because we are bringing together the best of the Altair Technology Conference as well as the Siemens SimCenter Day. Okay, so the whole focus is on how to handle the sheer complexity of the modern development, the product development. So basically, using a unified platform to combine simulation-driven design with the latest AI workflows. It's like, a very great chance to see how to speed up the design cycles and actually get products to market faster than the competition. So, Sujit, if you can share the link with the attendees, it would be great in the chat box.